Welcome to Easy BTech. I am Nawaz. In this video, we are going to learn about this analysis of propped cantilever. Okay. We'll take this problem. This is a propped cantilever with multiple loads. One is UDL and another is point load. The point load is acting exactly at a node. So let us assume this is my A, this is my B. So how do we solve this? The first step in analysis of any proper cantilever is to find out its degree of static indeterminacy. So first step, find out degree of static indeterminacy. So how many reactions do I have at support here? So since this is fixed length, we have horizontal reaction, vertical reaction, and moment. So we have three reactions plus. What about how many reactions at support B? We have only one reaction. Minus number of equilibrium equations. How many equilibrium equations we have? 3. So solving this, the degree of static indeterminacy we'll get is 1. Now, the second step is to find out its reactions. So since we need an additional equation, we need to develop this additional equation. So this step, developing additional equation. So how to develop this? So here we are going to use this principle known as principle of superposition. What do we learn in the principle of superposition is that, so if we have a structure, we'll convert that structure into simple structures, such as like this. Since this is a structure with complex structure, what we'll do is, initially, first we'll take is a simple structure, a simple cantilever with UDL of 10 kilonewton per meter. We'll analyze this, we'll get the deflection from this. Then in the second step, we'll take a simple cantilever and along with a point load that is 8 kilonewton at N. We'll get the deflection at this. Then in the third step, what we'll do is we'll take a cantilever with a reaction RB. We assume this one has a loop acting upward direction. We'll get the deflection. So since at the point B the deflection is 0, we equate all the deflection of these three simple structures equal to 0. From that, I can evaluate what is my RB. Okay, we'll do the same here. So first structure which we'll take is a cantilever with UDL. Here 10 kilonewton per meter is the intensity of this. This is my A, this is my, okay. Now I need to get the deflection. So deflection will be like this. So this will be my deflection. So I will represent it with delta 10. So what is the formula for this? The deflection. Delta 10 so the deflection is given by W L power 4 by 88. this will be negative because the deflection is acting in downward direction. Okay. Next, so we'll first solve this, we'll get the deflection, then we'll second structure. So now delta 10 equal to, substituting this value, minus 10 into, so here the distance is, 6 meters. Here to the same distance is 6 meters. Now 10 into 6 over 4 by 8 EA. Since we don't know the EA value, we'll leave this as it is, and the value here which we'll get is minus 1620 by EA. Okay, this is the deflection of cantilever with UD. We'll move forward. So we'll take second beam, that is cantilever with point of 8 kN. The distance here is, before drawing distance, let me draw the deflection diagram here. So deflection will be like this. This deflection I will represent it by delta 8. Okay, and deflection which is given here is, at this point is delta 8 equal to P L cubed by 3L is the formula. Now substituting this value, so delta 8 equal to, what is my P? P is nothing but my 8. So minus 8, length is 6 cubed by 3L. So solving this, I'll get minus 576 by EA. So this is my another deflection value. Okay. So let us proceed with the third one. That is the deflection due to the reaction RB. Here the deflection will take place in opposite direction like this. So here this I will represent it by delta R. Okay. So delta R is given by same thing, minus PL cubed by 3A. Substituting this value, delta R, instead of minus P, I'll write R, B, L is nothing but 6 cubed by 3A. So solving this, I'll get delta R equal to 72 RB by EA. This will be positive. Why positive? The deflection is acting upward direction. So I'll highlight this. Now I have got the three reactions. Now we need to develop that additional equation. What is this additional equation? So in proper cantilever, remember that the deflection at RB at B equal to 0, right? This point here. So we need to calculate. So we are getting a deflection at the free end. Whatever we have calculated values here. So these three values are at free end. Now, but all summation of all this should be equal to 0. So we'll do the same thing. delta V is nothing but the deflection due to the here plus deflection due to the 8 point load, that is 8 km, deflection due to the reaction R should be equal to 0. So what is deflection due to 10? So if we go and see the value, it is, this is the value, minus 1620 by EA. So I'll write it down, substitute this value, minus 1620 by EA plus, what is delta 8? That is deflection due to point. It is nothing but minus 576 by EA. So minus 576 by EA plus, what is delta? That is nothing but 72 RB by 3A. So it's not 3, it is EA. So this will be equal to 0. Now, sending these two values on the right hand side, so we'll get 72 RB by EA equal to, the value will be, the value we'll get is 2196 by EA. So EA will get cancelled and I will send the 72 on that side. So this will become RB equal to 196 by 72. This will be, RB value will get it as 30.5 kilonewton. I'll highlight this. So we have got the reaction at RB. Now we need to find out the remaining 3 reactions. What are the remaining 3 reactions? Let me draw this figure here once more. So we have this cantilever. At this point we have RB. Here at this fixed end we have horizontal load, vertical load and moment. Right? So we need to calculate this RA, HA, is MA. Now, since we have this equilibrium equations, what are those equilibrium equations? That is sigma fx equal to 0, sigma phi equal to 0, sigma ma equal to 0. Using these equations, we need to find out the remaining 3 reactions. So first step, so this is finding the reaction is the third step of this. Okay, in third, EA part is sigma fx equal to 0. Since there is no horizontal load acting for the point load, this is 8 kilonewton and this is 10 kilonewton per meter. Since no horizontal load is acting, so HA equal to 0. Going to B step, that is sigma Fy equal to 0. Let me select another line. Now we need to, here what does this second equilibrium equation mean? All the vertical loads will be equal to 0. What are the vertical loads we have in here? It is, we have reaction RA plus RB going upward direction, it will be positive, and minus 10 kilonewton of this value is 6 meters. Of 6 meters, the load of 10 kilonewton, it is acting throughout the beam, that is 6 meter beam. Since it is downward direction, it will be negative, minus 8 kilonewton. It will be acting negative, that is equal to 0. I'll send these values on the other end. So RA plus RB equal to, this will be 60 and this will be 8. I'll substitute the RB value here, which we have got here is 30.5 kilonewton. I will send that 2 on the other side, 68 minus 30.5. So it gives rise to RA equal to 37.5 kilonewton. And so this is my second reaction. Third reaction. This is also a reaction that is 0. Now the third 3C. What is the third equilibrium equations I have? Sigma MA equal to 0. What does this sigma MA equal to 0 mean? If you consider any point throughout the beam, if you consider any point throughout the, if you take the moment is nothing but load into distance at any point, then the value at that point, summation of all the moment at that point is nothing but it should give 0. Okay, let us take the moment at A point here, since we need to find out the reaction here. So now MA is acting. Before finding out moment, I need to clarify one thing, that is, we need to take, there is a sign convention. You would have studied in strength of materials. If you are standing in the middle, and if you take moment from the on the right hand side, all the moments acting in counterclockwise will be equal, will be positive, and all the values moment acting in clockwise will be negative. Same thing if you are standing here and you are trying to take the moment on the left hand side, then all the clockwise moments will be positive and all the counterclockwise will be negative. This is known as sagging moment. This is known as sagging moment. Right? Same thing here. Since here it is acting in counterclockwise direction on the left hand side, MA. So this will become negative. Okay. And take the moments here, since RA is acting at that point, that is 0 distance, RA into 0, 0. So we'll ignore this. We'll take, will come from the right most end. So RB is acting, that is acting in counterclockwise. Counterclockwise, it goes in the opposite to the clockwise direction, right? So it is positive RB into 6. Next, 8 kilonewton is acting. It is acting in clockwise direction of 6 meters. So load is 8, acting at distance of 6 meters. 10 kilonewton is acting. Its magnitude is 10 into 6 in clockwise direction, so negative. So 10 into 6 is the magnitude. At what distance? From the center of gravity, we have seen that if the load is UDL, then it will act at the half of the distance. So it will be 6 by 2. 6 by 2. This is the moment that will be equal to 0. Draw a line. So solving this, I will send the MA on the other side. So MA will be equal to RB is 30.6, 30.5 into 6. This will become 8 is 48 minus, this will become 128. Sorry, this is 180. Solving this, the moment we'll get is 45 kilonewton meter. Okay. Now I have found out the reactions. Let me plot these reactions here now. So how will the reactions look? Let me just so this is how it looks. So we have found out 45 kilonewton is a moment. Okay, RA is, this is my RA, it is 37.5. This is my RB. So this is how you need to draw these reactions. After the reactions, what is the fourth step? Fourth step is drawing shear force diagram. How to draw this diagram? It's very simple. What you need to do is first draw the diagram of this. Okay. This is my UDM. This is my point load of 8 kN. This is my 10 kN. And this is 6 meters. So this is my A. This is my E. Change my ink. Plot the reactions here. So this is my RE. It is 37.5. And this is my RB. It is 30.5. So we'll go from left to right. First is on the leftmost end. Draw this. On the left hand side, I have a reaction of 37 kN. So since it is going upward direction, draw this one. We need to give the value in the direction. Its intensity is 37.5 kN. Okay, this is my point A. This is my point B. Now coming back to the point B, we don't have any center point. We can take the point if you want, but let us directly go to the point B. At the point B, how to find out this shear force at. So at x equal to 0, my shear force at A is equal to 7.5 kN. At x equal to 6 meters, my shear force at B is nothing 37.5 minus, so this is reaction, minus the load coming onto this. That is how much load it's giving? 10 into 6. 10 to 6. So this will give me minus 22.5 kN. So here the shear force is coming in downward direction, opposite direction. The sign indicates the same thing. Okay. Now I will join this one. This will be my positive. This will be my negative. Okay. This is how we need to do this. But we also need to find out the point here. This point where my shear force is equal to 0. Why do we need to find this? Why? Because this is the point where we'll get the maximum bending. So what we'll do is we'll write the equation in the same form. How to do that? It is simple. So I'm writing the equation. That is, we have so 37.5 is reaction, we don't have in terms of x, minus 10 into x. X is ranging from 0 to 6. Okay. If we substitute the 0 value here, this is my SFX. If I substitute the 0 value here, I'll get 37.5. And if I substitute 6 value here, I'll get 22.5 kN. Now, this, if shear force is 0, okay, I will write for maximum bending moment, shear force should be equal to 0. So I'll make the shear force 0, change the ink. So this will become 37.5 minus 10x equal to 0. Now I'll like to find what is my x value. So x is nothing but 37.5 by 10, that is x equal to 3.75 meters. So at x equal to 3.75 meters, my maximum bending, I'll get the maximum bending.